Let's do an example of a bond. We have a zero coupon bond, no dividends. R is just the zero coupon bond rate. The equation is just the derivative of S is equal to R times S. Again, R is not the risk-free rate. It's just the rate for this bond. Well, dividends are zero, so we get a simple equation to solve that the derivative is a multiple of S. So we know that S is an exponential function. And in fact, we have a boundary value. We know what A is. A is any constant. For any value of A, the function S of t here will solve that equation. That's a simple calculus calculation that you can perform. And however, A is determined by some boundary value. A differential equation tells you how a function changes. And typically, in order to get a unique solution, you need to specify either where that function starts or where it ends. If you specify either boundary condition, S of 0 or S of capital T, then you get a unique solution in many of these differential equation cases. So if I specify the terminal boundary condition, S of capital T, then the unique solution to that differential equation that, in fact, achieves that unique boundary condition at the terminal time is given by this function. And again, it's easy for you to differentiate this function to confirm it satisfies the equation, and then it's apparent if I plug in little t equals capital T that it works. As an example of a dividend stock, a dividend-paying stock, we can also integrate, which is the general term used for differential equations. Sometimes people will say we integrate the differential equation, meaning we're solving it. But the differential equation can be solved, and there are various tricks to solving differential equations that we don't need to go into. But it's certainly not difficult for us to confirm that this is the solution. And this is a solution of the stock equation that has a terminal value specified of S of t. So what we can see is that if I plug in capital T for S, the integral becomes 0, and I just get S of t. So this is the solution to the differential equation that has value S of capital T at time capital T. Now, we can check that this satisfies the differential equation. I'll just remind you how one differentiates. And the key idea is that if we start off with the answer, S of t is equal to the integral from t to capital T of d of s e to the minus r s minus t dt. And then we have s capital T e to the minus r of t minus t. Now, you may have forgotten how to differentiate an integral. And the basic idea is that we have two values of, this is ds. We have two values of t in this integral. We have a lower limit of integration, and we have a function of t inside the integrand. So the general approach to doing such an integral is that if we take the derivative of s with respect to t, if you have a t in the upper or lower limit of integration, what you need to do is to evaluate the integrand at that value of little t. If the little t is in the upper limit of integration, I just insert it into the integrand. If it's in the lower limit of integration, I use minus the value of the integrand at little t. So the first step is noticing that I have a little t in the limit of integration, and when I take a derivative of an integral with a t in the limit of integration, if it's in the lower limit, I use minus, and then I simply evaluate the integrand with s equals t. If the little t was in the upper limit of integration, I would do the same thing, except without the minus. So I take the integrand, I evaluate it at t, little t, and I put a minus in front because it's a lower limit of integration. The next step is I can take a derivative inside the integral. So I still have the integral from t to t. And now when I take the derivative with respect to t of the integrand, I end up with just an r times the original integrand. Because I'm integrating with respect to t, remember. And then when I take a derivative of this last term with respect to t, I just get r times the value. And what we see is that ds dt is minus the dividend plus, and I can factor out an r, and what I see is I get the expression for s. So indeed, the derivative of the stock price plus the derivative plus the dividend value is equal to r times the stock price.